In this video, we're going to be discussing a Bernoulli problem with stagnation. So let's go ahead and get into the problem statement. So we can see we have two different tanks of water with streams coming out of them that are interacting at point A, which is a stagnation point, and we're asked to determine H, which is the height from point A to the top of tank 2. And a stagnation point is where a point where the fluid's velocity is going to equal exactly 0. So we can see here that we have two different streams and they're going to have actually equal and opposite velocity. So that at this point exactly, point A, it's going to cancel out with a net velocity equal to 0. And that kind of means conceptually that this point, this mass of water where it's interacting, is not going to be moving up and down in this way. Again, the velocity is going to be equal to 0. Also in this problem, you'll note that the original dimensions were given in feet as well as PSI. I chose to convert these into SI units just because that's a little bit easier to deal with, that I don't have to worry about having pounds per square inch and height in feet, for example. But feel free to convert it as however you like, as long as you're making sure you're consistent in your equation. Then, although I told you that we're doing a Bernoulli problem at the beginning, it's important to be able to determine for yourself what kind of a problem you're dealing with, especially on exams. So, thinking about the Bernoulli equation, we can see that it describes streamline flow using different terms. So, we have velocity, pressure, and height, all of which we can see in this problem. And we also know that at the stagnation point, velocity is equal to 0. So that's going to cancel out. It's going to be really great to use Bernoulli's in that situation. Additionally, with Bernoulli's, we always deal with streamline flow. And again, we have a key hint here, which is that we're dealing with streams of water. So again, pretty clear that we're going to be using Bernoulli's in this case. The next thing we can talk about is the assumptions. So we want to be using an ideal fluid. So we're assuming it's inviscid, which we also know from here, and incompressible. Although there's an elbow at this point, we're assuming that there's no head loss because we haven't been given any values. We're also assuming that the pressure at point A as well as the top of tank 2 is going to be equal to 0 because it's exposed to the atmosphere. And we're assuming that the density of water equals 1,000 kilograms per meter cubed, as well as the fact that there is still water in these tanks. And now that we have these assumptions set up, the next thing you should think about is how exactly can I apply Bernoulli's? We know we have an equation, and a lot of times this is on the formula sheet, and you see it, and you want to make sure you know how to use it. So with Bernoulli's in this form, we're comparing two different points along a streamline. So we want to think about what are the critical points in the problem that we have. And we can see that it's usually going to be where we're given different values, where we know different information. So this is going to be one critical point, right? We're given the height of 8 feet as well as the pressure. Of course, the stagnation point where our velocity is equal to 0. That's going to be super important because, as I mentioned before, our velocity term in Bernoulli equation is going to cancel out there. Then we also have the top of tank 2, right? We have to make sure to include that because we have that height term right there. We wouldn't be able to use any points along here. And the reason for that is because we're not given any values, right? We would just end up with an equation full of constants that might be more complicated, and we wouldn't really be able to solve for the height. So we know those are the three critical points, and we want to be using or describing those with our Bernoulli equation. The next question is, well, how many Bernoulli equations do we need? Are we just going to have one where we're going to be describing or comparing two of the different points? Or are we going to have multiple Bernoulli equations that describe different sets of points? And in this case, the key to remember is that Bernoulli describes two different points along a streamline. And when we look at these two different tanks, well, we have two different streamlines. One is here, and then one is here. So because of that, we cannot compare this point with this point because they're two different streamlines. So instead, our option is going to be to pick two or to set up two different Bernoulli equations. One is going to compare the stagnation point as well as the top of tank 2. That's one stream. And the second point is going to compare tank 1 and then the stagnation point. So two different Bernoulli equations. Let's get into the first one. We can describe the top of tank 1 as well as the stagnation point. So taking a look over here, I'm going to rewrite this. Let's go ahead and keep the left side as 0.1. So we'll have P1 again. times rho g plus velocity at the top of the tank squared over 2g plus the height of tank 1. And keep in mind for this problem, all the heights are going to be relative to the ground since that's how they're defined. And that's going to be equal to, instead of P2, let's go ahead and say PA1. So the terms are going to be for that stagnation point, specifically for streamline 1, not the streamline 2, streamline 1. So PA1 over rho g plus VA1 squared over 2g plus ZA1. And then we know that our head loss is equal to 0, so that term is going to cancel out. Then the next thing we know is that the velocity at the top of the tank is going to be equal to 0 since we have still water. So that means we're going to be canceling out this term right here. The next thing that we know is that you'll notice in this problem, we have a gauge pressure. And remembering what that means is it's going to be the absolute pressure minus the atmospheric pressure. And what you'll notice in this setup is that P1, well, this is going to describe the absolute pressure of that point 1. And PA1 is actually going to be this point right here, which is exposed to the atmosphere as we talked about before. So that's actually going to be an atmospheric ATM, atmospheric pressure. So knowing that we have P1 and PATM, but we're given gauge pressure, that hints to us that we're actually going to be combining our terms. So let's go ahead and write this as P1 minus PATM over rho g plus Z1 equals VA1 squared over 2g plus 2A1. Now that we have this, we can go ahead and plug in our different values. So this right here is going to be the gauge pressure in the numerator, so 172.369 times 10 to the third over rho, which is 10 to the third, times 9.81, plus Z1, which is the height to the top of tank 1, so 2.44 meters is going to be equal to VA1, which we don't know as of yet, over 2 times 9.81 plus ZA1, which we are given as 6.096. And now that we have this set up, we can see this will cancel out. And now we can go ahead and use our calculators and solve for VA1, which is going to be about 16.523 meters per second. Next, since we've solved for a value, we can go ahead and address that second tank. So let's go ahead and rewrite our Bernoulli equation, and I'm actually just going to move this one over here. So similar process here. Let's start by simplifying the equation. And instead of P1, we're actually going to be dealing with, again, PA2, right? This time we're talking about that stagnation point with streamline 2 right here. And again, we don't have head loss in this equation. And then the right side is going to describe this point right here at the top of tank 2. Again, we can cancel out the velocity at the top of the tank since we know it's still water. And then we also know that both the pressures, actually the pressure here as well as at the top of the tank, since it's exposed to the atmosphere, they're both going to be atmospheric pressure. So this is going to be PATM and again PATM. Since we have two of the same terms here, they're going to cancel out, which simplifies our equation greatly. And we can now go ahead and start plugging in our different values. So we have velocity A2, which we don't know yet, over 2 times 9.81, plus our height at the stagnation point. So that's going to be 6.096 equals the height at the top. And in this case, we're going to be using h. Remembering that this is all relative to the ground, this is going to equal h plus 6.096. And we can see that these two are going to cancel out, which means H equals VA2 squared over 2 times 9.81. Now that we have solved for H, we want to figure out what we can plug in for VA2, or the velocity at that stagnation point. Well, remembering that the net velocity at that stagnation point has to equal 0, right? These velocities are going to be equal and opposite. And in this case, this is our VA1, and this is our VA2, and they should be equal and opposite. So knowing that VA1 equals 16.523, that's going to be the exact same thing. We can say VA1 equals VA2 in this case. So we can go ahead and plug this in, and we'll have H equals 16.523 squared over 2 times 9.81. And then solving for H, we should end up with 13.915 meters, or 45.653 feet. And that pretty much concludes the problem. Thanks for watching.